to xye to the negative x negative y. Not a problem. This is symmetric, guys. If it's symmetric, that means that your partial derivatives are the same. Right?
Of course.
Now, to find the derivative here won't be... It's a little bit more involved, but you'll manage. I hope you used product rule. Listen, they're always right. We have the product rule. When I'm taking the derivative in respect to x, I can regard this as one function and this as the second function. And y's would be constants in this case. So copy the first, which is xy, times the derivative of the second. Well, the derivative of e would be itself times the derivative of the exponent, which is -1, plus copy the second, which is e to the negative xy, and then times the derivative of the first. The derivative of the first, since we are taking the derivative in respect to x, the derivative of x is 1, so the constant y is the only thing that we have. And now we simplify this. So fx is going to be, I will write the y term first because the second one is negative because of -1. So y e to the negative x minus y minus xy e to the negative x minus y. Now it's very important to factor, right? You factor because you need to set each one of those equal to 0. So fx is equal to, I can factor out y e to the negative x minus y, and what's left is I factored out everything from the first term, so that's 1, and in the second term only x survives because y is factored out. So there is my fx derivative, and now fy derivative, because function was symmetric, I'm going to swap all x's for y's. So this would be x, e, the exponent will remain the same, and then 1 minus y. So I'm just going to say by symmetry. So how do you know that you have a symmetric equation? This is very important for this section and for the next section. You don't want to sit there and figure out the same derivative for 20 minutes when you have, especially the next section, Lagrange multipliers, you might have 3 equations, and to find the derivatives is just, right? So symmetry is to be exploited anytime you can, and you know that the equation, right, the equation is symmetric if you swap x and y and you get the same equation back. So that's how you know, and that means that the first and the first partial derivative of both kinds will have the same equation if you just swap x and a y. And that actually goes for any dimension because, you know, equation x, y, z is symmetric. Equation x squared, y squared, z squared is symmetric. X, y, z, e to the negative x, negative y, negative z is symmetric. Sine of x, y, z is symmetric. So anytime when you are able to swap x for y and y for z and z for x, and you get the same equation back, the equation is symmetric, and then you will have the same partial derivatives. So now we have this, and we set each one of these equal to 0 to find critical points. So the first one equal to 0, the second one equal to 0. So what happens here is, on the first one equal to 0, we get 3 equations. Y equal to 0, e to the negative x minus y equal to 0, and 1 minus x equal to 0. So this is what happens when you set the first equal to 0. Now, this one is already solved, so y equals 0, that's that. This one has no solution because the exponential function never cuts through x-axis or y-axis. So that's that has no solution, and clearly the one at the end is x equals to 1. So from the first equation we already have a critical point 1, 0. Right, critical point 1, 0 is already with us. Now we solve the second equation here, second set, and we get the same stuff. X equal to 0, e to the negative I equals to 0, and 1 minus y equal to 0. And we get, again, this is solved already, so we're good there. The second one has no solution, so no solution here either. And the last one over here is that y is equal to 1. So that's another one of these. And we are back. We have another point. 0, 1. Now, remember how equations are linked? Where you have your fx equals fy equals to 0? Right? What? What's funny? So now you see that this creates a pair as well, and that creates a pair as well. So in addition to these points, we also have to check 0, 0 and 1, 1. We might throw those away, but we might keep them, right? So when you find your partial derivatives and you set everything equal to 0, you are going to have a whole bunch of x's and y's. And they can, combinations of those are going to give you also points that you need to consider. So now we are going to consider 4 of these points, and then some of these we might have to throw away. I don't know, we'll see. Now we are going to take a look at the second derivative. Now, when you're looking for fxx and fyy and so on, you do not want to go into these simplified factored versions, because when you have factored versions, that means product rules, right? So go to the vanilla case over here, actually here, and take derivative from there, because you might not have to worry about multiple product rules or nested product rules. You will have only one product rule at the time. So it just happened in our equation here to have a single product rule on x. But what if this y was x as well, right? If this y was x, then over here you would have xy creating a single product rule in this term, and this would be x squared. Again, single product rule within the term, right? But what would happen on the bottom? You would have a triple product rule, because x would show up here, here, and here. And that's a triple product rule. So if you are looking, this is just a quality of life suggestion, right? As you are looking for the second derivatives, do not go into simplified factored equations, because you might end up with a triple and quadruple and so on product rules, because these equations should be bad and long and so on, because that's what this is. So we are going to go here. I'm going to rewrite this equation and then work on the second derivative. What's happening over here? What was that screen copying? Oh, it's still syncing? Come on, Microsoft, don't fail me. I will have to chisel. Copy. I've never seen this screen copying. I copied a million times. So, how's life? What's new? As we wait. I could, but I could also wait. Come on. Ah! There we go. See? All you need to do is to think positive. All right. So now we need fxx. I need this. I think that the software is protesting. So fxx, all right, fxx. So now I have, the first one doesn't have the product rule because we are taking derivative. So we just go y, it will be negative y, e negative x negative y. And now over here we do have product rule. So copy first times the derivative of the second times, plus copy second times derivative of the first. And now we simplify. So minus y e minus x minus y minus plus x y e minus x minus y minus y e minus x minus y. There we go. So now these guys combine. We have negative 2y e negative x negative y plus xy e negative x negative. Oh, this is awesome. And then fxx. You had the choice not to have the exam. This is next Thursday, so right. Y e negative x negative y, and then x minus 2. Perfect. There we go. Woo! So that's that, which means that fyy better be x e minus x minus y of y minus 2. That was easy, but nowhere close to being done because we need fxy. Remember that part? Now that derivative you always have to take, symmetry or not. So now fxy, fxy, so taking derivative in respect to y, you're going to have two product rules, right? Because it's y times this, and then again y times this. Now, you could avoid that by actually using the factored form, because then you would have to only do one product rule, because the second part would be 1 minus x, and that is constant in the eyes of y. So now, I'm actually first going to fix that. This will be y e to the negative x negative y times 1 minus x. So I'm using the factored form for this derivative, because I only have to deal with one product rule, and this is a constant that I copy for fxy. So fxy, copy the constant, that's 1 minus x, times, and now we do the product rule. Copy first, derivative of the second, plus copy second, times derivative of the first. There we go. Now fix this. We have 1 minus x times, in parentheses, we can factor out e to the negative x negative y. And when I factor that, I get 1 minus y. And that's that. So now what do we have? We have to compile our d, which is fxx, fyy minus fxy squared. That means that the whole thing over here has to be squared eventually. No, don't worry, we got this. We got this. We'll be done by 3 p.m. with this example, and then we can finish up the second part of this lecture in time for me to have my 4:30. So don't panic. If you have doctor's appointment at 2:15, just cancel it, obviously, because you're not going to make it. So d, which is the function of x and the y, is going to take our fxx. Fxx was y e to the negative x, negative y, and then in parentheses x minus 2. That needs to be multiplied by fyy, which would be x e negative x, negative y, y minus 2, and all of that minus, in parentheses, we have, well, we can just square each one individually. So 1 minus x squared, 1 minus y squared, and then e minus x minus y. Yeah, it's squared. There we go. It's squared. So now d of xy is equal to, I have x, y, x minus 2, y minus 2, and then e to the negative x, negative y squared, minus 1 minus x, 1 minus y, both of those are squared, and then e minus x minus y squared. Now you see that you can factor out this e, right? The beautiful thing about this, it looks crazy, right? It's fine, right? It looks crazy. But please observe that you can factor out e term squared, and that's going to be positive all the time. So that doesn't, right? And we only care whether d is positive or d is negative. And we know that e part cannot be 0. So there is this part analysis there that you actually don't have to compute everything, right? You can simplify to the point where it's usable and work with smaller part of this equation. So e to the negative x, negative y, everything squared gets factored. And now in this big bracket is the rest. Now, for that part, I'm going to actually distribute x into x parentheses, have x squared minus 2x, and then y squared minus 2y. And then from that, I'm subtracting these guys, which is the product of 1 minus 2x plus x squared times 1 minus 2y plus y squared. There we go. And I only need to deal with the algebra of polynomials. I don't have to worry about e piece, because e piece is always positive, and that will not impact at all equation. Again, we don't care about the value of d, we only care whether it's positive or negative. So this is always positive. Therefore, we can even just not write it. It will not change anything. But we'll keep it for the sake of completeness. What do I have here? Well, now this needs to be FOILed. So I have x squared y squared minus 2xy squared minus 2yx squared plus 4xy. As you can see, guys, your algebra efforts are not wasted, right? Years of practicing, because we get to exercise it here. Now the next part will have 9 terms, because you are multiplying trinomial times trinomial, so that has to have 9 terms. So that's going to be 1 minus 2x plus x squared. Now we have to multiply with negative 2y, so that's going to be negative 2y, positive 4xy, and negative 2yx squared. Perfect. And now times y squared, so that's plus y squared minus 2xy squared, and finally plus x squared y squared. And now I'm going to do something that I never do, but I have to, because it's just so much writing. I'm going to change all of the signs in the parentheses, so I don't have to write. So I'm going to remove the parenthesis and change every sign inside. And now I can simplify. Who picked this problem? So I have xy, this one, gone. Minus x squared y squared, gone. This one and this one, gone. This one and this one, gone. And the rest survives. I have 1. Now it's negative 1. Negative 1 plus 2x minus x squared plus 2x. No, not 2x. 2y. Please pay attention. And minus y squared. Perfect. So the entire thing collapsed just to this one parenthesis over here. And this is the one where we are going to check our 4 points. We have 4 points now to check where your ABs are given by 0, 0, 1, 0, 0, 1, and 1, 1. That will give you your D's, right? Now also, before you go and compute these, I like to compute fxx real quick. Oh no, that's gonna be, not compute, I mean to write fxx here. So fxx is right there, y e x minus 2. Y e x minus 2, perfect. So now I see both equations, I see all 4 points, and I can go and say, okay, for point 0, 0, for point 0, 0, I have D of 0, 0. Now observe that E would be e to the 0, which is 1, so does not contribute. We have D to be just focusing on this part. So when I plug in 0, 0, everything dies except negative 1. So D is less than 0 and saddle. As soon as you have D less than 0, it's saddle immediately. Let me go back to the green definition. And as you can see, when D is bigger than 0, you get min and max. When D is smaller than 0, you get saddle. We cool on that? You have to memorize green, otherwise, I know. Next.
You have to keep going.
You have to. We did 25% of the problem so far. So let's go. 75% left. I mean 75% of the answer. So now we have D of 0, 1. Whatever order you do this in, doesn't matter. So now your Y is 1. And everything with x will die. Now look, you're going to get e to the negative 1. E to the negative 1, guys, is 1 over e, and that's still positive. The first term is always positive. I am not going to look at it at all. I don't care, right? It's always positive, so it only depends on the second part, whether it's positive or negative, because positive times positive is positive, positive times negative is negative. So whatever the second term is, right, the second factor is, then that's what the whole D will be. So now what survives? Minus 1, x term dies, this one dies, plus 2, and then minus 1. That's a 0, right? So test is inconclusive. The next point that we are considering is 1, 0. By symmetry, it should be the same. 1, 0. So now we have negative 1 survives, plus 2, minus 1. The other ones die, 0, inconclusive. And the last one is 1, 1, which is D. So that's 1, 1. And 1, 1 is when I plug the, so that's 1 plus 2, minus 1, plus 2, minus 1. So that's minus 1, 3. Everything is 1. That's larger than 0. Okay, so now we have d larger than 0, which immediately prompts us to compute fxx at 1, 1. We need to compute that. So fxx computed at 1, 1 is going to be 1 times the positive e, we don't care, times 1 minus 2. So that's going to be negative 1. Well, it's not going to be negative 1. It's going to be negative 1 times 1 over e. So negative 1 over e. That's what it is. I'll write the thing. So it works out to be negative 1 over e. That's less than 0. So this is what? Very good. So we have a saddle point at 0, 0. We have a maximum at 1, 1. And the test is inconclusive for 0, 1, and 1, 0. Now, for those, you can go and compute additional points around and check whether they are min or a max. So if you get the mixed response, it's a saddle point. If all of the points are bigger than what you have over there, it's going to be minimum. If all the points are smaller, you're going to have. That was problem 22. After that, no, 24, right? After that, there's 25, 26, 27, 28. They have square roots. They have inverse tangent. And all. You know, the inverse tangent is not that bad, right? You get 1 over 1 plus x squared y squared. And then you get take the second derivative, and the second is partial derivative. So the looks you just got. And then after problem 28, you have problem 29, 30, 31, and so on. Having some wonderful examples, like problem 32 will take a year to differentiate. And this is why we have technology, right? Because if you take a look at problem 32, it's pretty much the problem we did now, except it just has this sine y added at the back. so that makes a triple product rule. But again, nothing that you can't handle, right, on Sunday. I mean, right? So there you have it. So second part of this lecture, this is the best part when I say that, right? Is going to be figuring out for finite objects, things that you can pick up, right? Whatever you pick up is going to have the guaranteed max and guaranteed min. And those values can be detected. So those values can be detected by doing all of this, obviously, for the inside of the domain. But then you have the boundary. And the highest point could be at the boundary. Boundary is the edge of the shape. So if I am to take this desk and lift it on its side so that this little edge over here, oh, there's a cable. I can't do it because there's a cable that goes through the thing, so it can't. Anyway, I can do it with a printer. So now, looking at the box right over here, it's flat on the surface. There's no max value on it because it's flat, right? But if I stand up one of the edges like this, and it stands on the edge, now you have this point here. This point will not be detected because it's on the edge. Will not be detected by the method that we did. So what we have to do is we have to do more work. What we are going to do is, well, let's see. In a problem of a square or a box, you will have 4 sides. So you think of a box, and then you have wavy edges, right? So the box itself might have min and max in the middle. But at the edge, you also can have min and a max if the edges are shaped differently. So you have to do 4 Calculus 1 optimizations for each of the edges, and you have to do all of this for the middle. So this technically doubles or triples or quadruples the problems that we had so far. Because on top of what we just did, we have to do 4 Calculus 1. Or if it's a triangle, right, or circle, we have to do more of these optimizations. So let's take a look at that. Some of your facial expressions are just priceless at this point. So now min-max points can occur on the boundary. So I want to think about closed bounded sets. This is just mathematical way of saying you can pick the object up, right? Because you cannot really pick up the infinite shapes that we talk about most of the time. Previous problem was an infinite shape. It is not something that you actually, you cannot put this equation into the 3D printer and expect an object to come out because it's not bounded. So none of the shapes that we did so far are bounded. What is the bounded object? The bounded object would be the watermelon, right? So ellipsoid is the bounded object, but everything else on that list is not bounded. It's going to go to infinity in some sense, somewhere. So now we can bound the object, and we bound the object by providing the domain, the region. As soon as you cut the region under the infinite shape becomes bounded and becomes a 3D object that you can pick up. So they have a graphic in a textbook for the problem they did. So this was an infinite plane that was bent into a parabola. That's what it is. But then they decided to have a triangular, as you can see, the triangular domain, which immediately, what you need to think about is a stencil or a cookie cutter, all right? So you have something like this that is bent. This particular shape that I just bent a piece of paper, right, in a parabolic shape. Now, when you're looking at this, the 2 edges that are hitting my hands on the bottom will go infinitely down through the planet into the space forever. Further, the parabola edge that you see and a parabola edge that I see will hit my face, will hit your face, and it will extend indefinitely in that direction as well. So this is infinite in all of those directions. Now, what happens is, if I shine the light above this piece of paper, there will be a shadow on the desk. And that shadow is the domain, and that shadow is a guarantee that the shape that I'm holding is actually a finite shape, which is the reason why I'm holding it. There will be no way for me to pick up this object and hold it if these edges were going forever down and the front edge and the back edge over here were going forever in those. How would I grab it? Like, maybe I would be able to grab it like this and hold it, but as you can see, it kind of slides out. So as soon as I shine the light above this object, it will give me some kind of rectangular domain, and that rectangular domain is actually, you can think of a stencil that it's pressed upon the infinite cylinder that I have. Press that stencil in, and then it just gives you the cutout of the shape. So now when I have that stencil cut, which is the domain which is going to be given to you, is going to define, when you intersect that with the equation of the shape, that will define these edges and make each one of these edges Calculus 1 optimization problem. So now if you look at the shape this way, you have the side that has no min and max on it because it's a flat line. The same one on the other side. But if you look at these guys, there's the absolute max. And if this is, let's say, angled, you would have absolute max. These corners would be absolute mins. And you would detect them when you do the parabola on the other side. These would become linear lines. Line segments that has a bottom point and a top point. Right? So there are a lot of geometrical things that you can do. So now, what would be the umbrella? The umbrella is that infinite elliptical, well, circular, paraboloid, right? That it's like 9 minus x squared minus y squared, with a circle stencil that it's pressed on it to cut off the infinity that goes forever with that equation and bound that so you have actually an umbrella. That's what it is. So now you need to think about cookie cutters, right? If you haven't done anything with those, it's time to order them online and play a little bit at home to make sure that your Calc 3 is going well. So let's take a look at example of this. And as I mentioned earlier, this introduces a lot of new calculations. So let's see. Problem 54 says that fxy is equal to. I'm doing the cheapest problem they have because I want to be done with this today. I have class in 3 hours, so. Region R, which gives me the stencil, are all x and y points in the domain such that absolute x is less than 1 and absolute y is less than 2. So that's your region R. So fxy is x plus 3y, and this is a plane. You can't get cheaper than this, right? The plane is going to have 4 corners because plane is at the angle, right? Some of those corners are going to be max, some are min. But anyway, let's go and do this. First, I have to unleash the procedure of the middle, right? So we do what we have done so far. Find fx, which is 1. Find fy, which is 3. Set them equal to 0, and you get no solution. Because you can't have 1 equals 0 and 3 equals 0, right? Since you have that situation, no solution, that means no critical point. Now this is good because at least we don't have to do this. All right? Yay. But now we have to deal with the boundary as well, because boundary is given. If this was an infinite problem, so without this, right? If this was an infinite problem, you are done. You are going to claim that this plane does not have min and a max. You have to immediately imagine this cover that I'm holding at some angle like this in space, extending infinitely in all directions. You will never have a min or a max. However, as soon as I take the cookie cutter and press it on that infinite plane, I get the bounded plane like this. Now that bounded plane at this angle, look, has absolute max and has absolute min. You see that? So the difference between the problem that has this bound and not have the bound is that every time when you have this bound, you are guaranteed to have min and a max because you have the object, right? It's there. So it must have maximum, has to have minimum, right? So now we go and we deal with that. First off, what is this notation absolute x less than 1 and absolute y less than 2? What is this? Well, if you think about it, you draw your domain. You see that x's are bounded between a -1 and +1, and y's are bounded between +2 and -2, creating the region of your cookie cutter, of your stencil, all right, that cuts. So this is your region R. R. I know. So now, these edges give you equations. This edge over here is equation x equals to 1. This edge on the other side is x equals -1. The top is y equals to 2, and the bottom is y equals to -2. These equations will help you to reduce your three-dimensional problem down to 4 one-dimensional problems, and you can unleash Calculus 1 to find the critical points and to find min and max for each one of those. So now I'm going to say x equals 1. So when x equals to 1, your function fxy, which was x plus 3y, becomes a function z equals 1 plus 3y. I hope you see that this is your now Calculus 1 equation, because you have a single input and a single output. Yeah, I understand it's not xy, right? But it's yz, whatever. So you are going to have yz and you're going to have xz, right? Z is playing your y in this case. So now you have this, and now this is Calc 1 optimization. Now for Calc 1 optimization, you know that you are supposed to take the derivative and set it equal to 0 and do all of that cool stuff. However, if you do that, your derivative will be 3. You set 3 equal to 0, it will again say no solution, right? But hold on. You are on the finite region over here, and you have these endpoints. You have the endpoint on the bottom, which is 1, -2, and on the top, you have 1, +2. So you can compute your z values, right? You can compute your z values at y equals -2. So you are computing this at -2, and you will get 1 plus 3 times -2 for the total of -5. And z at 2 is going to be 1 plus 3 times 2 for a total of 7. So, min, max. So min value occurs. That's just, guys, for this x equals 1 line. For x equals 1 line, because it's at the angle, right? The bottom part, the bottom is the minimum, and the top is the maximum. This is just one line, right? It's 1 plus 3y. 1 plus 3y is going to be some kind of line in space, and you're going to have minimum point, and you're going to have maximum point, because length of that line is 4, right? From -2 to +2, length is 4. So if this is 4, you have the minimum point here, the maximum point there. So those minimum point, this minimum point over here occurs at x is equal to 1, y is equal to -2, and z is equal to -5. The max value occurs at 1, 2, 7. We are done with x equals to 1. Let's go. X equals to -1. Your function z equals f of xy equals x plus 3y becomes z equals -1 plus 3y. Again, compute z at -2. Z at -2 would be -1 plus 3 at -2 for a total of -7. And z at 2 is -1 plus 3 times 2 for a total of 5. So now this is your min, this is your max. Min is at -1, -2, -7, and the max is at -1, +2, +5. Two more lines. We have a line y equals to 2. When you have line y equals to 2, your equation z equals f of xy equals x plus 3y becomes z equals x plus 6. So now you are computing z at -1 and z at 1, because those are the x values that you have. So z at -1 is -1 plus 6 for a total of 5. And +1 plus 6 for the total of 7. The points are starting to repeat, because obviously those are the same corners you had before. So now this is some kind of a min, and this for this section, and it happens at x equals -1, y equals to 2, and z equals to 5. And the max, which is happening at x equals to 1, y equals to 2, and z equals to 7. You see it right here? And you see it right here. Right? It's the same point. It's where those two corners meet, and that's when at the angle, that will be the top one. But we'll analyze that later. I just wanted to point out that that point was around already. The final calculation is the fourth side, y equals -2. When you have y equals -2, your equation z f of xy will become z equals x minus 6. And now we have z at -1, which would be -1 minus 6, which is -7. That is going to be minimum eventually. And see, this is going to be local max, right? But it's, again, and this is happening at so x is -1, y is -2, and this is -7. And this is happening at x is equal to 1, y is -2, and -5, right? Now, remember, we did not have any solution, any critical points, any min-max values in the middle of the shape, right? Because it's a plane, right? If the plane had a little hill, right, or a hiccup or something, then the middle part would detect that. And then that would be in our mix of points. But since it's just flat like this, there are no min or max, so that's why none of those equations had solution to it. So we had nothing in the middle. What happens next is you look at all of these 8 points. Well, some of them are repeated. There's actually 4 points there, but you have 8 points. And you look for the ones that have the highest z value. So your absolute max is at the highest z value. And that's where you have positive 7. But if you take a look, positive 7 is given here, and a positive 7 is given there, and that's the same point, 1, 2, 7. So 1, 2, 7 is absolute max. How about absolute min? Well, that's the lowest of all z values, and that's where the negative 7 happens. I know I have another negative 7. There it is. And it's negative 1, negative 2, negative 7. Negative 1, negative 2, negative 7. So, as I said, in the interest of time, I did the shortest problem possible. These problems can take long time. They are amazing for killing time and developing carpal tunnel. So, you guess what the homework with 10 of these would look like, right? It's called Weekend Gone, right? that's what. And Lagrange next, I was about to say next semester, Lagrange next class is going to be possibly even longer than this. So yeah. There it is, in all of its glory, right? 12.8, min and max problems. Next time you're tutoring someone in algebra and then tell you that the problem of 5 lines was too long, right? And just leave. That's, every time, right? All right, I'll see you at some point in life, which is Monday.